Hello everyone, welcome back to this online class. Today we are going to look at Fourier cosine transform as used in solving second order partial differential equations. In particular, we are asked to solve the boundary and initial value problem given by our PDE is the one-dimensional heat equation, and the domain for x is from 0 to infinity, and the time t is greater than 0. The boundary conditions, we know that u partial x when x is 0 is equals to negative u naught. U naught is a constant. Also, we are told that the solution u of xt approaches 0, and partial x also approaches 0 as x approaches infinity for all time t greater than 0. The initial condition at t is equals to 0, our solution is 0 for all x greater than 0. So in this case, we are going to use the Fourier cosine transform. Why? The reason is that you look at the boundary condition at the starting point at the lower end. And I told you, I'm still going to write a note, the choice between when to use the Fourier cosine transform and the Fourier sine transform. So you check the boundary condition at the lower end. If the condition is this one, u of 0t, if this is given, then it means you use the Fourier sine transform. If instead you're given u subscript x of 0t, then this will mean that you use the Fourier cosine transform. So it is the boundary condition at the lower end that will tell you on which transform to use. Of course, I told you that Fourier cosine and Fourier sine transforms, they are applicable when your domain is semi-infinite. You see here, from 0 to infinity, this is a semi-infinite domain. And now look at our boundary condition at the lower end at 0, x is equals to 0. We know the velocity boundary condition. So we are going to use, this will guide us, this will tell us that we use the Fourier cosine transform. So what I've explained here is very important. At times you might not even be told to use whichever transform. It's up to you to decide that which transform can I use. You can just ask you to use an appropriate transform to appropriate Fourier transform to evaluate the given boundary and initial value problem. And I also told you that the complex Fourier transform is applicable when your domain is infinite domain, where it extends from negative infinity to positive infinity. So having explained that, let's now answer this question. Now that we know we are going to be using the Fourier cosine transform, so we say let FC, f subscript c I mean, be the Fourier cosine transform operator. It is operating in the variable x. So the first step 1, we are going to operate with f subscript c, the Fourier cosine transform operator, on both sides of the PDE. So what are we going to get? It will be the Fourier cosine transform of partial u partial t is equals to the Fourier cosine transform of k times second partial derivative of u with respect to x twice. So I ought to have explained here that the K here is thermal diffusivity. In this case, it is a constant which can be factored out. So what is the transform of the left-hand side? Remember, our transform is in the variable x. So when you transform the derivative with respect to t, this is what you need to get. You need to get derivative d dt, now ordinary derivative, of the Fourier cosine transform of u of x t. That's what you need to get on the left-hand side. On the right-hand side, k can be factored out so that will multiply the Fourier. This should be Fourier cosine transform. The C there means it is cosine transform. So you need to ask yourself, what is the Fourier cosine transform of the second derivative of u with respect to x twice? That will give us negative u subscript x at 0t when x is 0, then minus omega squared times the Fourier cosine transform of u of xt. That's what you need to get. Remember the definition of the Fourier cosine transform. So that's where you get it from. Let me write a note, just in case you need to know how we define the Fourier cosine transform of a function. So the Fourier cosine transform of u of xt is equal to the integral from 0 to infinity. Then we have cosine of omega t, that should be omega x, not t, cosine of omega x times the function u of x t. And you're differentiating with respect to x. That is the definition of the Fourier cosine transform of a function. Now, let's see, we are given the boundary condition. So the second step, you can write here step 2. You write apply the velocity boundary condition. Velocity because we have differentiated u with respect to x. So that boundary condition at the lower end, right, at the lower end. The lower end, I mean when x is equals to 0. What is u? So we are told u subscript x when x is 0, that is equals to negative u naught. U naught is a constant. So this one here, this one should be equal to negative u naught. So you see it will cancel with the other negative so that we have positive u naught. So therefore, this equation can now be written as, this means that d dt of the Fourier cosine transform of u of xt is equals to k outside. Then inside we have u naught minus omega squared times the Fourier cosine transform of u of xt. That's what we have. Let me rearrange this. This is an ODE, so let me rearrange it. You can write or d dt of the Fourier cosine transform of u of xt. I want to bring this to the left-hand side, this one. So what will it be? It will now be a plus. So there's a plus k omega squared Fourier cosine transform of u of xt. On the right-hand side, now we have k times u naught. U naught is a constant. Now, this is ODE of the first order. It is linear in the Fourier cosine transform, or you could also solve it using the d operator method. So this equation, this is an ODE. So we can use the d operator method. Of course, it is linear. Also, you can solve as a linear ODE using the integrating factor method. But I find d operator method is easier for me. So I'm going to say let d be derivative with respect to t. So this means that our equation can now be written as d plus k omega squared operating on the Fourier cosine transform of u of xt should give us k u naught. Now, we are going to find two solutions with the complementary function and the particular integral of this equation. So we start by finding the complementary function. In this case, we need to solve d plus k omega squared operating on the Fourier cosine transform of u of xt to give us 0. Now the auxiliary equation is d plus k omega squared is equals to 0, of which you can be able to find the root, just one root, make d the subject, negative k omega, and this is a real root. This is real because k is a real number, omega is also a real number. So how do we write our solution? So therefore, the complementary function is now equal to, we call it C1, an arbitrary constant, exponential negative k omega squared t, where C1 is an arbitrary constant. Let's find the particular integral. You need to make you need to divide both sides by d plus k omega squared. So it will be 1 over d plus k omega squared operating on k u naught. K u naught is a polynomial of degree 0. Polynomial of degree 0. So what does it mean? That you check the degree of those d operators, the power of the d operators. If you find that the power is greater than the degree of the polynomial, then it is advisable that you drop such kind of terms having the powers which are greater than the degree of the polynomial. So you look at our d operator, it is d raised to 1. 1 is greater than 0. So what will I do? I will drop this term, that d operator, so that what I have here is now 1 over k omega squared times k u naught. And so this can be written as u naught over omega squared, because you see k will cancel with the other k. In fact, let me simplify here. K here will cancel with this. So we have u naught over omega squared. Now, To find the general solution, we simply need to add the two solutions so that we can be able to find our general solution. So we'll say that therefore the general solution is simply equal to the sum of the complementary function and the particular integral. So you can say, or the Fourier cosine transform of u of xt is equals to a constant c1 exponential negative k omega squared t plus u naught over omega squared. So that's what you get. Now, what is the other step? You need to find the value of the arbitrary constant C1. So what we do here is to apply, you see already we have applied the boundary condition. We still have the initial condition to apply. I'm going to apply this initial condition. Ux0 is equals to 0. Already these have been catered for. You see this and this other condition, they have been catered for when you are getting the transform of second derivative of u with respect to x twice. So the last condition is that initial condition. Let us apply it. So that will be step 3. So we write here step 3. Apply the initial condition. So what do we say? That u of x0 should be equal to 0. So you need to take the transform on both sides. So we write Fourier cosine transform of u of x0 should be equal to the Fourier cosine transform of 0, which is equals to 0. So that means in this equation, look at the one I have ticked. When I substitute t is equals to 0, I am supposed to get my transform on the left-hand side to be equal to 0. So we will say now, therefore, 0 is equals to c1 times exponential 0, which is just 1, then plus u naught over omega squared. And so we can now make c1 the subject. So from here, you get that c1 is equals to negative u naught over omega squared. So that's the constant, the arbitrary constant, which we now know its value because we have applied the initial condition. So let me replace it in that equation, this one. So you can just say that hence the Fourier cosine transform of u of xt should now be equal to negative u naught over omega squared times exponential negative k omega squared t added to u naught over omega squared. And this you can as well write as, if you see u naught over omega squared is common, so this can be written as u naught over omega squared times 1 minus exponential negative k omega squared t. You can just say or Fourier cosine transform of u of xt. So that's what we have. The last step is to find the solution u of xt. So we operate with fc inverse. Take the inverse transform on both sides. So you write step 4. You operate with fc inverse. This is fc, f subscript c, on both sides. On both sides of this equation, the one that I am bracketing, that's what you need to operate on. Remember, fc inverse is the inverse Fourier cosine transform operator. So when you operate with it on the left-hand side, what are we going to get? On the left-hand side, we are going to get u of xt. What about the right-hand side? It is fc inverse of u naught over omega squared times 1 minus exponential negative k omega squared t. Now, how do we define the inverse of Fourier cosine transform? So let's take note here that the Fourier cosine transform, the inverse of that one, the inverse Fourier cosine transform of any function of omega, call it u of omega t, is defined as 2 over pi times the integral from 0 to infinity, 2 over pi times the integral from 0 to infinity of that function that you're finding is inverse, that is u of omega t, u of omega t, then cosine omega x d omega. And that will give you a function of x and t. So therefore, when we go back to our inverse transform, this can now be written as 2 over pi, the integral from 0 to infinity u naught over omega squared 1 minus exponential negative k omega squared t, as the function that we are finding is inverse, then times cosine of omega x d omega. And you see u naught is a constant, so this can as well be written as 2 u naught over pi, the integral from 0 to infinity of 1 minus exponential negative k omega squared t times, this is over omega squared, times cosine of omega x d omega. So if you have time, you can also be able to evaluate this integral to get the final answer. But even if you leave your answer as this integral, then there's no problem. So that is the solution of that particular boundary and initial value problem. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems on Fourier cosine and Fourier sine transforms. Bye-bye.